Hi all, welcome to Theoretically Podcasting. This is Vasu Sham, and today I wanted to cover a textbook calculation which I thought was very neat when I first understood it. But I think it has very interesting implications when thought of a little bit more carefully. So the calculation is that of the leading contribution to the beta functions of a conformal field theory perturbed by a relevant operator, uh, computed through conformal perturbation theory. And what this calculation shows is how there's data in the conformal field theory in its very definition that knows about the deviations away from the fixed point. So that's one of the basic things that really struck me as interesting when I understood it. And also, I'll go over some relatively recent work by Schrimmer and Thiessen about understanding what happens when the story is modified by irrelevant operators, and in particular, what a metric beta function is. So I'll go slowly initially through the literal textbook version of the calculation that I first encountered in Cardy's book, Scaling and Renormalization in Statistical Physics, specifically in chapter 5, titled The Perturbative Renormalization Group. And having gone over this calculation, I will jump to the paper by Schrimmer and Thiessen, where they talk about the connection between conformal perturbation theory and the Osborne equation. The Osborne equation is the thing that featured in a previous episode about the local renormalization group. But here we'll see how it needs to be modified when in fact we're considering irrelevant operator deformations, and that the modification involved actually involves running of the background geometry, as it were. And so to begin, let me start with a very simple introduction to the whole setup. And again, just following Cardy's book, what we have is basically the situation where we're looking at a partition function of some lattice model near a renormalization group fixed point. So it's a fixed point under Kadanoff block spin transformations. And if you consider adequately long wavelength fluctuations, they behave as if they're in a continuum field theory. So there's numerous approximations one needs to keep track of to make sense of the various manipulations that will follow. I will do my best to mention them, but we will see how we can do without a number of these approximations when we have a more modern perspective on the problem. So Cardy starts with the partition function of a CFT. So H star here defines is basically the fixed point Hamiltonian. And we're really putting this theory on a lattice. So the perturbation he considers is by generic sum of primaries. So he wants scaling fields, as he calls them. So they're basically primary operators that have a correlation function on a flat space that has power law behavior, right? So that's an important component. And so there's the sum over the indices of the primaries themselves, and then there's this sum over, well, this is basically going to be replaced by a spatial integral. Basically, you have some expression like this. That's what, in some sense, defines the partition function of the deformed theory. Now, what he does is says, well, you can kind of replace this with an integral because details of the lattice are irrelevant anyway. But note that in order for the dimensions to come out right, we need to include the short distance cutoff A in these integrals, and we need to take into account the scaling dimensions of the operators in order to really have something dimensionless that we're integrating over. And here, the integral is really, it has a short distance cutoff, which is the lattice size, and then it has an IR cutoff, which is the size of, well, this is the extent of the lattice. So there's a lattice spacing and the lattice extent. And basically, we're going to be doing a sort of some version of finite size scaling. If we're really thinking about this in a principled manner, that's what this calculation is really going to track. Now, the first thing to do is expand this out in terms of correlation functions. So basically, what we're going to do is write this as the partition function of the fixed point theory. This instead is big. And then we're going to have the following sum. So this formal sum is going to define what we mean by the perturbation theory we're interested in. So first, we just have the leading term, which is going to know about the 1-point function. And again, if this was really on flat space, we would not have this 1-point function. We could just shift by the vev. But here, what we're doing is putting things in finite volume, and at least this is what Cardy says in the book, that in finite volume, you're not allowed to make this shift as carelessly. And this is something that we can do without, as we'll see in more modern treatments of the problem. But the advantage of having the 1-point function is that it shortens our calculation by length 1 in some sense, in terms of correlators involved. And I'll go over exactly what that means too. So we have a term that looks like this, and then we have a term which has the second term in the expansion, and we have a double sum. This is basically saying that there's a moment expansion for this object. So here we have two integrals, and again, all of these are rendered dimensionless through the careful rescaling by the cutoff dependent terms. And here we have the 2-point function. And then there's more stuff, as you can imagine, which goes like order G cube and beyond. So that's basically to give us a feel for what the expansion looks like. So basically G cube over 3 factorial and so on. So anyway, this is all we'll need to set up the calculation that we're going to do. So the calculation is really going to be what is the effect of doing a blocking and rescaling transformation. So let's set up what we mean by blocking. Blocking is A goes to BA, where B is some positive number. It's we'll take it to be 1 plus delta L. This is not equals, it's plus. And delta L is taken to be small. And then the question is what, okay, so how do we rescale, right? So how do we rescale our couplings, right? So in order to get back to the same partition function, more or less, but with redefined couplings, right? So this is the question we're going to answer. Now, there's some conventions that we need to bear in mind before going any further. First convention is that of the 2-point function. So here, these are primary fields. And so at the fixed point, which is where we're calculating all of these correlators. So really you should think, well, this is the wrong place to put it. Really you should think about these as being calculated within the fixed point. So we're allowed to use these expressions in our manipulations. That's kind of the idea. And so in Cardy's conventions, this is what he means. He has that right, so standard 2-point function. And the other thing to note is his convention for the OPE, right, between these primary fields. And so the leading OPE expansion. So he has, this might be slightly non-standard. He has a sort of midpoint prescription. So he basically has some OPE like this. You have this operator product a function with the following structure. And here he has that this is really at the midpoint. And this will also help in the calculation, having this prescription. R1 plus R2 divided by 2. Okay. And what this object is, at least for primary fields to leading order, the singular part is going to be set by the 3-point function coefficients. And here we're just going to have the separation. Okay, great. So we're armed with these facts, and the claim is that this is enough to know what the beta functions are going to be. In other words, it's enough to know how to answer this question, right? So this rescaling is still a question. Okay, so let's do okay. I don't even know what to call this. The zeroth order is the zeroth order, which is that the dependence that the partition function terms in the partition function have on the cutoff, so the explicit dependence is through these denominators. So very clearly, there's the following effect that needs to be taken into account. And this is an almost trivial one. So what we're going to have here is that we're going to have G be rescaled by an amount that's counter to what A gets rescaled by. So A gets rescaled to BA. So we're going to have B to the power D minus delta I in the denominator. So we want B to the power D minus delta I in the numerator. And really, when we take this to be 1 plus delta L to the power D minus delta I, and then when we take delta L to be small, this is going to be GI plus okay, so this is the zeroth, well, I mean, not call it order. It's really the zeroth contribution. It's part of the first order, really. So the zeroth step is just to keep track of the obvious rescaling that occurs through the explicit denominators. Now, the more interesting rescaling, the non-trivial one, comes from what happens within the integrand. So let's go now within integrands. All right, so let's dissect this term first. So let's take the second order term and rewrite it a little bit. And here, this is basically going to utilize the fact that even though we're writing these as continuum expressions, we imagine that there's really some sort of hardcore repulsion between these operator insertions set by the lattice. So in order to see that, what we're going to do is split this integral up, right? So instead of writing it in terms of R1 and R2, we can write it in terms of, well, the following. So again, let's just take the denominators out for a second. So I'll just write the denominator here. And what we'll do is write this as d of R plus and d of R minus. And I'll just keep the 2-point function as it is for now. Right, and then we can muse about some obvious facts. So okay, R plus and R minus are basically the sum and difference of R1 and R2. And now, obviously, there's going to be issues when we have r minus becoming very small, right? So whenever you write an expression like this integrated expression, in the back of our minds, we should worry about the regions where these two positions collide. So these two operators will collide. And that is isolated here in the r minus integral. So I could just, let's just do make it clear that this is a double integral. And so what Kaidi does is he says, okay, so here, what we really do is notice that there's actually a lower bound to this integral set by our cutoff prescription, which is that r1 minus r2 is greater than a. And then under rescaling, right, so I do this? Yes. And then what I really want to say is that under rescaling, which goes like a to 1 plus delta L A, we have that this integral goes to, sorry. So this integral goes to a having 1 plus delta L. And what we're going to do is write this in the following manner. We're going to write this as first the original integral. So we have the original integral over the separation, minus we have a shell integral. So we have greater than a, but then we have a times 1 plus delta L greater than this. Right. Is that correct? Yes. So we're basically removing from right. So we're basically removing this piece. Well, okay, we can write it like this actually. So it's a plus. So this is going to be, in some sense, the lower bound, and then we have the completion from the lower bound to the true upper bound. Well, so again, all of these are in the lower bound themselves, but I mean in the inequality here. So here, what we can do is see that because delta L is very small, and because we're going to basically take these two to be very close to each other, the integrand should be replaced by an OPE expression, right? So it should be replaced by the limit where R1 approaches R2. Right? So basically, we're going to take this, and we're going to take link. Yeah, I think that this really should be a minus. Yeah, sense. Okay, so let's do L angle here. Okay, and so what can I write this as? I can really write this in terms of the OPE expression replacing what's happening inside here. So what I'll have is actually phi k, and then I'm going to have C ijk of this very 1 minus 2, which now actually is approximately A, right? So basically we can have the OPE expression inside here, but the separation is so small that we really want to take R1 minus R2 to be of order A, of order the lattice spacing. And what's that going to be? Okay, well, I have not written the actual measure. The measure is minus. So this is basically going to be, when we do it, you just have C dash K. Well, what's going to end up happening is we're going to have A to the power delta K minus delta 1 delta J and I don't know 1 and 2. And then we're going to have basically the volume of the sphere here, which is I to the power. So basically from decomposing the integral into radial and angular parts in momentum space, we're going to have k of r plus. So this is the r minus is what we've integrated over, and then we still have the r plus. Plug this back into the total integral, and it's basically we're going to have the net effect. Right? So the net effect is going to involve C here with whatever's going on here. Okay, so there's also going to be an A to the power D because this is without the radius. So the radius contributes A to the power D. And yeah, so this is 2D. So the A to the power D will cancel when I plug this back into the integral. I'm going to have, let me just write this. So I have whatever was going on here. So this equals the original integral, right? Minus whatever's going on. So the original integral, so let me write this as with 2 A plus L. So I write this as the entire thing with the original integration bound minus the result of our manipulation. So we have only the r plus integral. And what else do we have? We have the sum ij, we have gi, gj, and we have c ijk. We have a to the power d divided by a to the power 2d minus delta I minus delta j. We have, in addition, the contribution coming from the actual B coefficient. So we have a to the power delta k minus delta I minus delta j. And so we also have that this is phi k r plus. And so we just see that there's a number of cancellations that happen here, and we can replace this this integral over r plus with just r. It's a dummy variable. But notice that this is contributing back to the 1-point function. So what's happened is that in doing the rescaling, the singular part of the 2-point function contributes back to the 1-point function. So we're going from this second order back to the first order, and you see that this is actually organizing itself quite nicely. So if I look carefully at what's going on, so okay, this is all proportional to delta L. If we really did everything carefully, it's a to the power d delta L. That's the size of this sphere, the radius. So here we have delta L. So this is why it's still first order. So I didn't want to call the previous thing the zeroth order because these are actually the same order. But this is second order in the couplings. If you wanted to think about it in terms of that expansion, it's second order. So here we have eliminated one of the integrals. We've basically gotten to do one of the integrals. And the result of all of this, right? So let's do the cancellations here. What happens is that in the denominator, I have to cancel. I get to cancel all of this. And I get to cancel this. I get to cancel these two. And then I take this delta k down. So I have 1, and then I make this d minus delta k. What do you know? It really fits perfectly into the format of the first order term in the expansion. Provided I rewrite r plus as r. It's a dummy variable. I'm integrating over it. I don't care. And so what have we accomplished? Well, what we've accomplished is that we've gotten, okay, so sorry, there's still a 1/2 factorial and the consequential sphere volume. So I can, yeah, SD, and that SD basically is, it is this entire thing. So well, let me just write it out since I've taken the pains to write it out once. So it's to pi to the power 2 divided by gamma of p over 2. Great. So what's happened is that we can now take this in with the rest. So in our partition, so the contribution this yields, right? So contribution to scaling is the following. So we had to rescale already gi by d minus delta I, gi, and now we have 1/2 of the 2 times sum k c ijk j gk. Oh, is that correct? I think that it's the other way around. It's gki. Yeah, yeah. The k is the one that's not summed. Okay, it's the first two indices that are summed. And again, this is all delta L. Okay, so now we have an expression for our running coupling, right? So now we can write our RG flow equation. And in the RG flow equation, we see that basically, okay, so here too we have a sum. Yeah, but whatever. Basically, in the RG flow equation, we have these contributions. So if I was to take this derivative with respect to L of gi, there's one contribution that goes like d minus delta I of gi. That's just the canonical scaling dimension. Then there's a second contribution, which looks like pi to the power d over 2. So I would trust my factors and signs very little. It's just saying. But basically, the important fact is that we have so the leading order in conformal perturbation theory, what we see is that the 3-point function coefficients contribute to the beta function. So in other words, beta function, right? So we define this to be beta I. of G. So our beta function has these two terms in it. So you see that the 3-point function coefficients that you would normally compute within the conformal field as part of the conformal data is actually also telling you what happens when you perturb the conformal field theory by that primary, if it's a relevant primary. So it's telling you how basically the theory flows. And I think that this is an utterly fascinating calculation, but there's the funny thing here, which is that we, had this 1-point function that didn't vanish. It was on the lattice, and we're secretly doing finite size scaling because what we're doing is we are rescaling G, rescaling A, right? But holding L, the size of the lattice fixed. So this isn't truly the thermodynamic limit. Right? So there's some IR subtleties, but this actually captures the essence of the true calculation, if you like, because instead of doing all of this with constant couplings and putting it on the lattice, you could do this with sources, so sort of like space-dependent couplings, and come to very similar conclusions. And to see how that works, I'll jump to this very interesting paper, which, in my opinion, didn't get the attention it deserved, but then again, who knows? So this is a very nice paper by Schirmer and Thiessen titled The Osborne Equation and Irrelevant Operators. So they talk about how, like we described in a few episodes ago, there's a general formula for the Weil rescaling, infinitesimal Weil rescaling of the generating function of a CFD or a perturbed CFD, meaning a QFD. And it has this format, right? So the format is, as a response to Weil rescaling, the couplings of the theory, when you upgrade them to sources, respond through their beta functions. So what does this mean concretely? Now, of course, the thing is that in general, the result of Weil variation also knows about the anomaly, and the anomaly knows both about the metric and about the sources, but there's no operators. So there's some non-operatorial contribution. But what does this strictly mean? So here they go over quickly the calculation we did in a little bit more detail. They say the role of the beta function can be made explicit in the lowest non-trivial order, right? So they say that this is the OPE when X and Y approach each other, and they say, well, look, there's secretly a logarithmic singularity hiding here. And if we take just this fact into account and then think about how we would actually write generating function, then we would see that actually we're going to have to include the singular behavior of OPE in both the 3 and 2-point functions. So in the 2-point function, we need to know what to do when these two get very close to each other, because we're basically doing these double integrations, and that's going to give us a term that looks like this. And then in the 3-point function, we're going to have the square of this, right? So basically, they say that we basically are going to have two possible coincidences, and here we're going to have one possible coincidence. And when you have a source, right, so this one possible coincidence is what gave rise to the kind of RG flow equations we were interested in before. But to see here what's going on, they very quickly show the result that we just derived. Right? So they say the singularity in the OPE is translated into the first non-trivial term of the beta function for the source JK. Right? So the Weil variation, when acting on this object, we think about the Weil variation as the variation with respect to the scale mu squared. And you see that the variation with respect to the scale mu squared is just one of this thing, and proportional to this here. Right? So this is what makes it such that delta sigma of jk, aka beta k, is sigma timesCijk, Jijk, exactly as we derived, up to some overall factors. And so this is the recursion relation that are underlying the perturbative validity of the Osborne equation, right? And they say that, you see, if you thought about this in momentum space, it's basically a sense that the correlators obey subtractive dispersion relations and a finite number of subtractions, and you only need a finite number of subtractions depending on the dimensions of the operators, and they control all the correlators. So basically for marginal and relevant operators, you need a finite number of subtractions. And then what they comment on is the fact that when you have irrelevant operators, the number of subtractions increases with the order. But at any finite number of irrelevant operators, the general structure of the Osborne equation will still be valid, because at any finite order, you just need a finite number of subtractions to control the logarithms. But if we're going any further, let's actually look at why are they even talking about logarithms here? And here's a nice section of Yanis Papadimitriou's lectures on holographic normalization that goes over it relatively quickly. So it's based on this idea of, you could do this in position space, right? Just the same way as they've shown. And then there's also a momentum space manifestation of it. And the idea is just based on differential renormalization. It's this idea called differential renormalization, where you start by looking at composite operators of dimension delta and their two-point function, and say that, well, okay, what can happen is that when this delta, okay, so depending on the conformal dimension, this correlator may suffer from short distance singularities. So consider this case where delta is half the dimension plus k plus epsilon, and epsilon is infinitesimal. Then you can actually do an expansion in epsilon by iterating the following identity. Right, so the statement is that 1 over x minus y to the 2 delta is 1 over this. Okay, so let's maybe confirm this at least in dimension 1, where I can go and do this on Mathematica. So let's see side by side what the two statements are. They say that there's symbolically, all right, it's like 1 over x minus y to the power of 2 delta equals 1 over 2 delta minus 1 2 delta minus d times box of 1 over, sorry. So again, Mathematica doesn't like this. This is just symbolic. This is not what I'll actually be using. 1 over square. So it's the square of 1 over x minus y, the power of 2 delta minus 2. So let's do this in a way that Mathematica can understand, at least in one dimension. So what I'm really going to compute here is 2 delta minus 2, and then I just take the second derivative with respect, say, to x. Right, and as you can see, I have these two factors appearing. So this is just a higher dimensional version where you would replace this second derivative with the Laplacian. Right, so that's basically the magic behind that. And then, okay, this is valid when x minus y is not 0, and we iterate that expression as Papadimitriou shows. And if you do this k plus 1 times, you get the following expression, which you can effectively write in terms of a purely local contribution. Right. Okay, so there's this very nice 1 over epsilon times this delta k of delta term. And they say, well, okay, let's try to renormalize the two-point function. And how would we do that? We would take epsilon to 0 and subtract this contribution, clearly, right? So they don't do it at this level. They just introduce a scale mu and then subtract the pole. And what they find is basically an expression like this. And so you have, for those dimensions, for those specific dimensions, you have the following contribution. It knows about k. K is in this scaling dimension. It knows about d. And there's the logarithm here, the promised logarithm. And in momentum space, you basically get an expression that looks like this. Okay, so those are the logarithms that they're talking about. There they chose some special operators. And again, so Schrimmer and Thiessen also comment on the momentum space structure of this operator. It's basically going to be here. So basically it's very similar without the epsilon. It's the same prescription that was there in the Papadimitriou notes. And they have basically the same expression with some scheme-dependent constant. And here they talk about how you can think about rescalings. Right? So you can think about rescalings. Okay, so here they say the explicit scale dependent signals a type P conformal anomaly. The two-point function transforms inhomogeneously under dilatations, right? And so basically they say this is what happens in momentum space on basically in flat space, but you can translate that to what happens when you introduce sources into your problem. And then you basically see that the quadratic contribution to the generating functional has the following structure. And under while rescaling, it gives us the following answer, right? And so you drop terms that vanish in flat space, and the basic form of the anomaly expressed as a violation of the void identity, which relates the correlator TOO to the two-point function OO, right? Because T is nothing but trace T is going to compute this. So knowing TOO will tell you all about this and all sorts of related contributions. And then they say, okay, let's think about this quadratic part. Right? The quadratic part will not contribute to the anomaly, right? So, or to basically beta function. So basically, or sorry, mainly to the beta functions, it can contribute to the anomaly. So they say to this quadratic order, the non-trivial part of the beta function of the sources cannot contribute, right? It can contribute maybe to the anomaly. And so here, if you did this on a curved background, you basically find that there's a generic structure like this, right? That you can try to figure out. And so you can use sort of cohomological arguments to figure this out. And what you get is that there's a special set of operators in any number of dimensions that basically give you the right scaling structure. And so for so when d equals 2, you get this. And d equals 4, you have this Riegert operator. And then if you add, basically some kind of relevant operator, then you have something ultra local in d equals 2 or in d equals 4. If you have a dimension 3 operator, you're going to have this differential operator. So that's all fine. And this doesn't contribute to beta functions. In other words, it's saying that there's no metric beta function. But that changes once you have basically irrelevant operators. Like once you have irrelevant operators, then for their sources, you can have basically some operator which does contribute to a beta function. And this is basically what they explain. So it comes from this very nice theorem of Glover and Hirachi, which shows that there exists such a differential operator with curvatures and everything else. And then basically they go on to do the analysis involving the TOO three-point function and show how you can explain that there's going to be a beta function for the metric, meaning that under the RG flow, it's not just a while rescaling, but really some geometric flow that the background undergoes. So I've been a little bit fast with this because there's a lot of details involved, but I just wanted to emphasize how there's this very nice connection where you can go from just lattice calculation, some kind of finite size scaling calculation on a lattice, all the way to a continuum calculation where you're being careful about what's going on in momentum space and so on, to a calculation involving general, sort of background sources and the metric and so on. So I thought this was a really fun little exercise to think about. And it'll be something that maybe I'll come back to and talk about in more detail. But for now, I hope you enjoyed this. If you've gotten this far, please like, share, subscribe. And I'll see you next week for another episode of Theoretically Podcasting.